Hello, I am Vinayak Solapurkar and you are watching YouTube channel Mathorich. The purpose of launching this channel is to share small videos with all of you. Friends, these videos will be on topics in mathematics, and basically I will prepare these videos for undergraduate and postgraduate students. The purpose of creating these videos is to share some small ideas which I like and I feel that I should share with all of you. In this inaugural session of Mathorich, I would like to share an idea which can be used to solve a problem in Putnam competition. Now, Putnam competition is a very old competition meant for undergraduate students in USA. It was started long back in 1930s. And this particular problem that I am going to discuss with all of you today also appeared, I think, in 1938. I will share references with you. And it uses an idea which connects apparently two different looking branches. And I like this idea, I like this solution. So let me make it clear that this solution is well known and I do not claim any originality on my part except for sharing this excitement of sharing this idea with all of you. So let me start with the problem that I am going to discuss with all of you. So the problem is like this. So let Px be a polynomial given by, say, a0 Px equal to a0 plus a1x plus a2x square plus a3x cube. Okay. So this is a cubic polynomial, and let us assume that the coefficients are real. So suppose all these a0, a1, a2, a3 are real numbers. Okay. Further, let alpha, beta, gamma be roots of Px. Now the roots would be complex. As all of you know, polynomial of degree 3 will have 3 roots and 3 roots in set of complex numbers. So these roots could be whatever, either real or complex, whatever they are. The problem is, find a polynomial whose roots are alpha cube, beta cube and gamma cube. So given a polynomial of degree 3 with real coefficients, and suppose its roots are alpha, beta, gamma, then problem is to find a polynomial whose roots are alpha cube, beta cube and gamma. So this typically sounds like a problem in theory of equations. So there are various problems of this type in theory of equations. That is, suppose find polynomial whose roots are squares of the roots of the given polynomial. Roots are alpha plus beta plus gamma. So many roots are reciprocals of the roots. So many problems you can pose of this particular type. Here we are asked to find a polynomial whose roots are cubes of the roots of the given polynomial. So definitely by using the techniques of theory of equations, that is finding symmetric functions of the roots. So we know the relation between coefficients of roots. So we know that alpha plus beta plus gamma is minus a1 by a naught, alpha beta plus beta gamma plus alpha gamma is a2 by a naught, and this Vieta theorem, relation between coefficient and roots, all of us know. So we can write those relations and find out alpha cube plus beta cube plus gamma cube in terms of a0, a1, a2, a3. So that particular technique can be used to solve this problem. So there is definitely a solution by using techniques in theory of equation. But what makes the solution that I want to share more interesting is that it uses an idea which is apparently coming from a different branch, and here the solution uses matrices. Solution uses matrices. Now, how do we form a matrix? So, given a polynomial like this, okay, there is a companion matrix. Okay, associated with this polynomial. So, for the time being, I assume that this coefficient is 1. Okay, so suppose Px is monic polynomial. So, assume that A3 is 1. So that the polynomial is monic. Then every monic polynomial we can associate a matrix which we can call as companion matrix of that polynomial. By that I mean that the characteristic polynomial of that matrix is the given polynomial. So I am writing now companion matrix of Px. Okay, so the companion matrix of Px is, let's call it as M. Okay. Now what is companion matrix? This is constant term. So so this will be 3 cross 3 matrix. So start with the constant term and write like this: minus a0, minus a1, minus a2. Take an a3 equal to 1. Assume that this polynomial is cubic, is monic, and then an identity matrix here, and 0, 0, 0. Okay. So the characteristic polynomial of this matrix is the given polynomial. Okay. So companion matrix means, so let me write it right here. The characteristic polynomial of M is Px. All of you know what is characteristic polynomial. It is determinant of M minus lambda. If you expand that, you get characteristic polynomial. And from this polynomial, this matrix is formed. So this is a monic polynomial of degree 3. Then I always get this matrix, and the property of this matrix is that characteristic polynomial of M is Px. Okay. Now I use the result from linear algebra that if eigenvalues of M are, now what will be eigenvalues of M? Eigenvalues of M must be alpha, beta, gamma, because those are roots of Px. But now in language of linear algebra, those are roots of characteristic polynomial. Means they are what? Eigenvalues of M. So note that. Alpha, beta, gamma are eigenvalues of M. Why? Because this is Px is characteristic polynomial of M, and roots of Px are given to the alpha, beta, gamma. So if I know the eigenvalues of M, then I also know that eigenvalues of M cube will be alpha cube, beta cube, gamma cube. So that is a result from linear algebra. That if I know eigenvalues of a matrix, and if I have a function f, say polynomial function, say of eigenvalues alpha, beta, gamma, then I can find out by forming that function of M. So suppose if I find out M cube, then I already know that the eigenvalues of M cube are going to be alpha cube, beta cube and gamma cube. Okay, so this is result from linear algebra, which I state in a slightly different way. So result from linear algebra. So if f is a polynomial function, let me take polynomial function here. Polynomial function. Then spectrum of Fm is equal to f of spectrum of M. General, this is a very general result, but I am using this for matrix M and polynomial function f. And by spectrum of a matrix, I mean eigenvalues. Okay, so when you have a matrix, its spectrum means eigenvalues. But I have stated in this particular language because those who are interested can search for this by stating spectral mapping theorem. Spectral mapping theorem. Okay. Now I can take f to be polynomial, say y cube. So I can always choose f equal to say polynomial y cube. Okay. Then f of m is m cube and spectrum of m cube is nothing but cubes of the points in the spectrum of m which are alpha, beta, gamma. Okay. So eigenvalues of m cube are alpha cube, beta cube and gamma cube. Those are eigenvalues of m cube. That means what? Alpha cube, beta cube, gamma cube are eigenvalues of m cube means the characteristic polynomial of m cube is the polynomial whose roots are alpha cube, beta cube, gamma cube. We precisely wanted to find polynomial whose roots are alpha cube, beta cube, gamma cube. That polynomial is nothing but what now? The characteristic polynomial of m cube. So the required polynomial is the characteristic polynomial of m cube. In general, so the problem is solved. Now point is that you need to find out characteristic polynomial of m cube, which can become complicated. But anyway, that complication will occur somewhere. Even if you find solution by using symmetric functions of the roots, that complication will be there somewhere or the other. So here you need to find out the characteristic polynomial of m cube. Okay, but this method can be used in general also if you have, instead of this cubic function, this f could be say y cube plus 3. So you can have some other function of m also. This method will work. And then symmetric functions of the roots, that method can be little more complicated than this. Okay, here you need to find out characteristic polynomial of a certain matrix. So m is given, finding f of m will not be a big deal, but then finding characteristic polynomial of that matrix, you may need to do something, work on this, and if the order is little higher, this will become further complicated and so on. But you can also think of various ways of computing characteristic polynomial. For example, given any matrix A, so you can use this result also. Okay. So how to find characteristic polynomial? One way is to expand the determinant a minus lambda I. But other way is to you can also compute principal minus of the matrix. So suppose for example A is n cross n matrix. Okay. So let A be an n cross n matrix. So you can use this in general. Okay. Now suppose Let me denote this, suppose by EK. Suppose EK denotes the sum of K cross K. Sum of K cross K, principal minus of A. Principal minus of A. You can go back and check what principal minus means, but that means minus, you can choose a subset of the index 1 to up to n and choose those rows and columns to form a submatrix and take this determinant. Okay, so you take all K cross K principal minus, find a determinants and take the sum. So that is what I mean by sum of K cross K principal minus. By that I mean determinants of those submatrices of order K cross K. Then characteristic polynomial is nothing but then the characteristic polynomial of A is given by, say, let me write something, say fx equal to x raised to n, it's a monic polynomial. The n cross n matrix I have taken, so it will be of degree n, minus E1 x raised to n minus 1. Can you identify what is E1? E1 is 1 cross 1 principal minus. That means entries on the diagonal. Sum of the entries on the diagonal means this is trace. This is E1 is nothing but the trace of the matrix. So this coefficient is trace plus E2 x power n minus 2 and so on. Now E2 will be 2 cross 2 principal minus. Okay. Just to give some examples, so suppose you have this A1 B1 C1, A2 B2 C2 and A3 B3 C3. Okay, then what will be 2 cross 2 principal minus? A1 B1 A2 B2, A1 C1 A3 C3 and A2 B2 A3 C3. So those are 3 cross 3. Okay, you can choose 1 2, 1 3 and 2 3. Okay, those will be 2 cross 2 principal minus of this. Okay, so 3 choose 2, there will be 3 principal minus of order 2 cross 2 like that, E2 and so on, minus dot dot dot, you can write minus 1 to the power n En. Okay, that will be constant term. Okay, now what is En? Can you identify En? En is n cross n. Minus, that means whole determinant, whatever you order n. So that is determinant of the matrix. So the constant term is minus 1 to the power n, determinant of this matrix. So characteristic polynomial can be expressed in terms of principal minus of the given matrix. So perhaps that technique you can use when you need to find the characteristic polynomial of whatever function of n. In this problem, in particular, it is m cube. Okay. So I like this idea because it uses some linear algebra. The problem statement is typically a problem in theory of equation. That is, some polynomial is given and you want to come up with some other polynomial. Okay. So directly there is no hint for using any matrices, linear algebra, but then the solution connects these two things by way of using this companion matrix. So this companion matrix comes into picture. Okay. So by learning this solution, students may learn several things and some simple application which connects the polynomials and matrices. That's why I thought that let me share this small idea with all of you. So thank you very much for patient listening. If you like this video, please like this or share this and subscribe to the channel Mathorich. Thank you very much.